Remember when I told you no matter where I go, I'll never leave your side, you will never be alone, even when we go through changes.
Our seventh topic is filtration. Under this, we'll talk about three subtopics. First one is the type of filters. Second is the grain size characteristic, and the third one is the filter hydraulics. So what is filtration? Filtration is the most often used as limiting step to remove flux and finer unsedimented particles through beds of granular materials. Filtration also removes suspended organic matters, microorganisms, and dissolved minerals from the water. There are two types of filter that are used. The first one is the gravity filters. The second one is the pressure filters. So let's start with the gravity filters. These are types of filters in which head is required by water to pass through the filter medium. This head is provided by height of water itself over the filter medium. There are two types of what we call the gravity filters. The first one is the slow sand filters, and the second one is the rapid sand filters. So slow sand filters, is effective size of sand particle is taken to be 0.2 to 0.3 millimeter. So head maintained at the top of the sand layer is equal to the depth of the sand layer. Design life of filters is equal to 10 to 15 years. Frequency of cleaning is 1 to 3 months. During cleaning top layer, around 1.5 to 3 cm of sand is removed. Rate of filtration is 2,400 to 2,800 liter per meter squared per day. The efficiency of bacteria removed in this filter is 98 to 99%. Sand slow filter should be used for small towns, village having population of less than 5,000. These are not used for water having turbidity of greater than 50 NTU. For our rapid sand filter, the effective size or D10 of sand is 0.45 to 0.75 mm. So surface washing alone is not sufficient, so we go for back washing. Amount of water for back washing is 2 to 5% of total water filtered. Area of tank is 10 to 100 meters squared per unit, and base material is gravel, and its depth is around 45 centimeters. The efficiency of bacteria removed in this filter is 80 to 90%. The rate of the filtration is 3,000 to 6,000 liters per meter squared per hour. The backwash period is around 24 to 72 hours, and the entire process is including the backwash, or the entire process of the backwash takes around 15 minutes. For a second type filter, we have the pressure filters. These are the type of filters in which the head requires for water to pass through filters medium is provided artificially by the application of previews over. The pressure filters with different complete unit is inside the closer chamber where flow of water is under pressure and not due to gravity. In pressure filter, water entering is either floculated nor sedimented. It is used for small-scale work such as houses, swimming pools, small-scale industries, and a lot more. So the rate of filtration is 6,000 to 15,000 liters per meter squared per hour.
For our phase velocity and loading rate, VA is equal to Q over A sub S, where VA is equal to the phase velocity, it can be the loading rate, and Q is equal to the flow rate into filter surface, and A sub S is equal to surface area of filter. As part of their proposed new treatment plant, Urban is going to install rapid sand filters after their sedimentation tanks. The design loading rate to the filter is 200 meter cube per diameter times meter squared. How much filter surface area should be provided for the design flow rate of 0.5 meter cube per second? And how large should the filter be if 4 filters are used? So our solution here, just have to rearrange the equation we had a while ago. So the surface area, or AS, required is the flow rate divided by the loading rate. So the flow rate is Q, and VA is our loading rate. So our flow rate will be divided by our loading rate, coming from our problem, and that will give us 216 meters squared. We also have, for the second question, if 4 filters are used, the surface area per filter is equal to our surface area divided by 4, and that is 54 meters squared. However, many states requires that the design loading rate be met with one filter out of service. In this case, we would need each filter to be, so you just, instead of using that divided by 4 answer that we had, so the surface area per filter should be equal to 72, because 216 meters squared divided by 3, and that is 72 meter squared. So, and that's our answer if we were to have 4 total. Because we generally don't design an odd number of filters, the alternative would be to use 6 filters with 1 out of service. Surface area per liter is equal to 260 meters squared over 5, and that's equal to 43.2 meters squared. Because filters can be 100 meters squared for even small plants, we would use a 4 filter design. Filter boxes are often built square, but cost minimization data such as filters should have a length to width ratio of 3 to 6. If we use a ratio of 3 width times width is equal to 54 meters squared, where the width is equal to 4.24 meter and 1 is equal to 12.73 meter. So if we had some loading rate leeway, we would make each filter 13 meter by 4 meter or 52 meters squared. Or if not, we could use around 13 meters by 4.2 meters, or we would go up in size to 14 meters by 4 meters. Now let's talk about grain size characteristics. Effective size is represented by big letter E, and uniformity coefficient is represented by big letter U. So our effective size is equal to P10, which is also equal to X sub G times S sub G, where X sub G is our geometric mean and geometric standard deviation is our S sub G. U is equal, or the uniformity coefficient, U is equal to the P sub 60 over P sub 10 equals S sub G raised to 1.535. So under filter hydraulics, we have the Blake-Hoseni equation. H over D is equal to K sub Z times mu times 1 minus E squared over density times G times E raised to 3 times A over R V squared times V. So where H is the head loss of depth in bed D, G is acceleration of gravity, A over V is the grain surface area per unit of grain volume, and mu is the dynamic viscosity of fluid, density is the mass density of fluid, Kz is equal to the dimensionless Hoseni constant commonly found to be close to 5 under most filtration condition, and V is the applied water velocity or loading rate. For our minimum fluoridation velocity, V sub mf is equal to mu over density D90 times 33.7 squared plus 0.0408 Ga raised to 0.5 minus 33.7 mu over density D90, where our Ga is the Galileo number and Ga is equal to D raised to 3 sub 90 times density times the quantity of density sub S minus density times G over a mu squared, where the density, the mu, G, is already defined above, and density sub S is the density of the grain, or which is sand or anthracite. Our next equation, we have here the Rose equation. So the frictional head loss through the filter is equal to 1.067 times the approach velocity squared times the depth of filter sand over shape factor times acceleration due to gravity times porosity raised to 4. Summation of I is equal to 1 of the drag coefficient times our mass fraction of sand particles of diameter d over our diameter of sand grains. Next equation we have here is the dE, which is the depth of the expanded bed, is equal to 1 minus the porosity of the bed times the depth of the bed before expansion, and summation I is equal to 1 of mass fraction of sand with expanded porosity over 1 minus porosity of expanded bed. The porosity of the expanded bed may be calculated for the given particle by expanded bed. A porosity of expanded bed is equal to velocity of the backwash over the velocity or the settling velocity raised to 0.22. Our first equation is another way to calculate the porosity of expanded bed, and that's only for laminar condition. And at the bottom we have here the Reynolds number, and it's defined as a Vs times D 60% sub 60% over the V.